The universe hides its most beautiful secrets in plain sight. Planetary nebulae are not planets, but the final breath of dying stars. We will explore 28 of the strangest discoveries that have completely reshaped our understanding of these cosmic wonders. You will learn how these stellar ghosts are rewriting the rules of stellar death. Why do some form perfect butterflies while others leave behind cosmic knots? What do you think is the most beautiful mystery in space? That beautiful name, Planetary Nebula, is astronomy's greatest misnomer. It all began with a simple case of mistaken identity. In the 1780s, the famed astronomer William Herschel, the very man who discovered the planet Uranus, was scanning the heavens with his telescope. He began noticing these faint, greenish, and often round glowing objects. Their disk-like appearance reminded him strongly of the distant planets he was familiar with, and so he called them planetary nebulae. The name stuck, but the understanding behind it was completely wrong. We now know these cosmic clouds have absolutely nothing to do with planets. They are, in fact, the final, glorious sigh of a dying star. When a star like our own Sun nears the end of its life, it swells into a red giant, and then violently sheds its outer layers into space. What remains is a super-hot core, a white dwarf, whose intense radiation causes the expelled gas to glow for thousands of years. So Herschel's planetary nebula is not a birthplace for worlds, but a stellar tombstone, a monument to a star's death. This foundational error set the stage for every surprise to come, proving that the universe often hides its most profound truths behind a familiar mask. But that stellar tombstone holds a furnace of unimaginable fury. The true heart of a planetary nebula is not the beautiful cloud itself, but the tiny, impossibly hot star at its center. When a star sheds its outer layers, it essentially strips itself naked, exposing its blazing core to the void. This leftover core, a white dwarf, undergoes a dramatic and violent transformation. It heats up to almost unbelievable extremes, reaching surface temperatures that can exceed 100,000 Kelvin. Some even push past 200,000 Kelvin. To put that into perspective, the surface of our own Sun is a relatively cool 5,800 Kelvin. These white dwarfs are, for a short cosmic moment, among the hottest objects in the entire known universe. And yet, they pack all that ferocious heat into an object roughly the size of our Earth. This creates a powerhouse of intense ultraviolet radiation. It is this invisible, energetic light from the tiny, searing core that slams into the expelled cloud of gas. The gas absorbs this energy and re-emits it as the visible, vibrant glow of reds, greens, and blues that our telescopes capture. The central star acts like a cosmic blacklight, illuminating the ghostly remains of its own destruction. Without that tiny, superheated engine, the nebula would simply be a dark, expanding cloud of dust, invisible to our eyes. The beauty is a direct product of the stellar violence. This violent illumination reveals forms of breathtaking complexity. Among the most spectacular is the Butterfly Nebula, a cosmic structure so vast and intricate it seems to defy the very nature of a star's death. For decades, the assumption was simple. A dying star would puff away its outer layers in a series of gentle, spherical sighs, creating a perfectly round bubble in space. But the universe had other plans. Nebulae like the butterfly, with its magnificent twin lobes stretching across light years, presented a beautiful and frustrating contradiction. How could a solitary, spherical star produce such a perfectly symmetrical, yet profoundly bipolar, shape? The answer lies not in a solo performance, but in a celestial duet. Astronomers now believe the secret is a binary star system at the heart of the chaos. As the primary star dies and expands, its companion star remains locked in a close orbital dance. The gravitational pull from this second star, and the swirling disk of material it can steal from its dying partner, acts like a cosmic nozzle. This system funnels the erupting gas into two powerful, opposing jets, sculpting the expanding cloud into those magnificent wings. The death of a star is not always a lonely event. It can be a violent, gravitational tango that carves the most beautiful structures in the cosmos. This breathtaking stellar artwork is tragically temporary. The very forces that create a planetary nebula also ensure its rapid demise. We are witnessing a cosmic performance that lasts for a mere 10 to 20,000 years. On the grand timeline of the universe, this is less than a single blink. The gas and dust, blasted outward at speeds of tens of kilometers every second, continue their relentless journey into the void. They expand and thin out with every passing moment, eventually becoming so diffuse that they fade from view, their glow extinguished as they merge imperceptibly with the interstellar medium. This fleeting existence solves a long-standing astronomical puzzle. Our galaxy is home to hundreds of billions of stars, a vast population all destined to pass through this phase. Yet we observe only a few thousand planetary nebulae at any given time. The math is inescapable. We are simply catching a tiny fraction of stars in this brief final act. The odds of having a front-row seat to this spectacle are astronomically low, making every nebula we can see a rare and precious snapshot of stellar death in progress. You have to be looking at exactly the right place, at exactly the right cosmic moment, to witness a star's last breath made visible. That brief, beautiful glow does more than just decorate the cosmos. It seeds the galaxy with the very ingredients for future worlds and, ultimately, for life itself. Planetary nebulae are the universe's master recyclers. Inside a red giant star, in the final million years of its life, the core becomes a frantic cosmic forge. The intense heat and pressure there trigger a process known as the triple alpha process, where helium nuclei, which are also called alpha particles, are fused together into brand new, heavier elements. This is how a star manufactures carbon, the fundamental building block of life as we know it. Other nuclear reactions create generous amounts of nitrogen and oxygen. For eons, these newly forged elements are trapped deep within the star. But when the star convulses and throws off its outer layers to form a planetary nebula, it is doing far more than creating a light show. It is launching these vital elements into the vastness of space, a rich cocktail of carbon, nitrogen, and oxygen that spews out into the interstellar medium. This enriched gas slowly mixes with other cosmic material, becoming part of giant molecular clouds that will one day collapse to form a new generation of stars and planets. Our own solar system was born from such a cloud. The iron in your blood, the calcium in your bones, the oxygen you are breathing right now, all of it was forged inside a long-dead star and then delivered to our cosmic neighborhood by a planetary nebula. You are not just living in the universe. The universe and the death of ancient stars is living in you. This cosmic recycling process begins with a stage so fleeting it was almost missed entirely. For a long time, astronomers had a straightforward picture. A star swells, it ejects its shell, and the hot core lights it up. But there was a gap in the story, a mysterious phase hiding in plain sight between the red giant and the glowing nebula. They called it the pre-planetary nebula, and its discovery revealed a crucial missing link in the stellar life cycle. In this brief window, the star has finished its violent mass loss. The outer layers are already out in space, forming a vast cloud of gas and dust. But the central star has not yet become hot enough to unleash the powerful ultraviolet radiation needed to make that gas glow on its own. So, for a few thousand years, a different kind of magic happens. The cloud does not generate its own light. Instead, it acts like a cosmic mirror, simply reflecting the steady, cool light of the central star. This creates what is known as a reflection nebula, often showing the same beautiful bipolar shapes we see in objects like the butterfly nebula, but illuminated with a softer, ghostly light. It is the calm before the storm, Then, the central star continues its relentless heating. In a final dramatic act, its surface temperature soars past 30,000 Kelvin, and it begins to blast out that intense ultraviolet light. This is the moment of ignition. The previously quiet cloud of gas is suddenly flooded with energy, causing it to ionize and erupt into the vibrant, glowing colors of a true planetary nebula. Catching a star in this pre-planetary stage is like finding a photograph of a firework the instant after the fuse is lit, but a split second before it explodes into color across the sky. Even stranger than the ghostly light of a pre-planetary nebula is the discovery of water shouting from the depths of space. In the seemingly hostile environment of a planetary nebula, where gas is blasted by intense radiation, astronomers were stunned to detect the unmistakable signature of water. This was not a gentle whisper, but a powerful, focused beam of microwave energy. The water molecules were acting as natural masers, which are the microwave equivalent of lasers, producing an intensely amplified signal that cut across the cosmos. This made no sense at first. How could fragile water molecules possibly survive, let alone thrive, in a stellar furnace that was tearing everything apart? The answer revealed a hidden architecture within the nebula. The intense maser emission could only originate from incredibly dense, sheltered pockets of gas. Think of these as tiny, shielded bunkers deep within the expanding cloud, places so thick with material that they could protect the water molecules from the star's destructive ultraviolet radiation. Within these safe havens, water could form and, when pumped by the star's radiation, enter a state of coherent emission, where all the molecules sing in perfect unison. This phenomenon turned a simple molecule into a powerful scientific instrument, a natural probe that allows us to measure the temperature, density, and motion of material in regions of the nebula we could never otherwise see. The water maser is a cosmic siren song born from chaos, pointing directly to the secret shelters within a star's final storm. That cosmic siren song of water points to hidden structures, but what force sculpts those shelters in the first place? For a long time, gravity and stellar winds were considered the sole architects of these nebulae. The role of magnetic fields was dismissed as negligible, a footnote in the story of stellar death. But then our telescopes got better, and we saw something that defied that simple explanation. We began to observe intricate patterns within the nebulae, with delicate jets and dense knots of gas that were not just randomly scattered. They were aligned, organized, as if tracing invisible lines of force. The discovery was undeniable. These structures were following the contours of powerful magnetic fields. It turns out the dying star carries with it a fossil memory of its past. The original star possessed its own magnetic field, much like our sun does. As the star convulses and sheds its outer layers, this embedded field is not lost. Instead, it becomes trapped within the expanding cloud of ionized gas. This process amplifies the field, twisting and stretching it into incredibly powerful and complex shapes. Think of it like a cosmic version of a spool of thread. As the star unravels, its magnetic field gets wound up tighter and tighter, creating a structured framework that guides the flow of the erupting material. This magnetic scaffolding provides a compelling new explanation for the bizarre forms we see. It can work alone or in tandem with a binary companion to channel the stellar winds, carving out the magnificent wings, rings, and filaments that leave us in awe. The most beautiful deaths in the universe are not chaotic explosions. They are carefully directed finales, sculpted by invisible forces we are only just beginning to understand. Those invisible magnetic fields give shape to the chaos, but they do not explain everything. Peering into the heart of these nebulae with the Hubble Space Telescope, astronomers found something that defied even their new models. They discovered knots. These were not simple clumps of gas, but strange, dense, fast-moving structures with a peculiar chemical signature. Scientists named them FLIRE, an acronym for fast low ionization emission regions. The name describes their bizarre nature perfectly. They are compact blobs of gas that move through the nebula at incredible speeds, often tens of kilometers per second faster than the surrounding cloud. Even weirder, they frequently appear in symmetrical pairs, positioned on directly opposite sides of the central star like two sentinels guarding a cosmic gate. Their low ionization state was the final clue. It means these knots are made of gas that has been spared the full brunt of the central star's intense radiation. They are somehow cooler and denser than the rest of the brilliantly lit nebula around them. So the mystery is profound. How can dense, cool knots of gas not only survive inside a stellar inferno, but actually race through it faster than everything else? One compelling theory suggests these flyer are not a late-stage phenomenon at all. They could be much older material, blobs of gas that were ejected during an earlier, more gentle phase of the star's death. Later, when the faster stellar wind from the hot white dwarf caught up with them, it could have swept them up and accelerated them to their astonishing speeds, like leaves caught in a hurricane. Another, even more dramatic idea points back to the binary star model. The flyer could be the result of powerful, focused jets shooting out from an accretion disk swirling around a companion star. These jets would punch through the slower-moving nebular material, carrying dense knots with them and leaving behind these symmetrical, high-speed anomalies. The existence of flyer proves that the death of a star is not a single, simple event. It is a story with multiple chapters, filled with earlier eruptions and late-stage accelerations that we are only now beginning to read. These fast-moving knots and intricate magnetic fields were just the beginning of the mystery. The true complexity of a planetary nebula remained hidden until we learned to see it with more than just our eyes. Our most powerful optical telescopes, like Hubble, capture stunningly beautiful images in visible light, showing us the vibrant glow of ionized gas. But that view is like looking only at the painted surface of a sculpture, missing the underlying armature and the form hidden within the stone. The great observatories, a fleet of space telescopes each designed to see a different part of the light spectrum, finally revealed the full, three-dimensional architecture of these stellar ghosts. What appears in visible light as a simple, perfect ring can be completely transformed when viewed in the infrared. The infrared eye of a telescope like Spitzer peers straight through the outer veil of glowing gas, seeing the warm dust that is invisible to Hubble. And in that infrared view, the simple ring often vanishes, replaced by a vast, bipolar structure, a hidden hourglass shape that tells the true story of the star's death. It turns out that many of the most famous round planetary nebulae are not spheres at all. We are simply looking down the barrel of a bipolar outflow, seeing the dense waste of the hourglass as a bright ring, while the vast lobes extend above and below, invisible to our ordinary sight. But the revelations did not stop there. The Chandra X-ray Observatory then looked at these same objects, seeing an even more energetic component. Chandra detected pockets of gas heated to millions of degrees, shining not with a gentle glow, but with the fierce energy of X-rays. This superheated gas is the signature of violent collisions. It marks the places where the fast wind from the newly formed white dwarf, racing outward at thousands of kilometers per second, smashes into the slower, older ejecta that was expelled earlier in the star's death throes. These colossal shock waves heat the gas to unimaginable temperatures, creating a faint, hot bubble within the beautiful, cooler nebula. This multi-wavelength approach shattered the illusion of simplicity. A single image in visible light is a beautiful lie. The true object is a complex, layered fossil record, with each wavelength of light uncovering a different chapter of the star's final explosive story. Even the most beautiful cosmic clouds are not as serene as they appear. The Helix Nebula, one of the closest and seemingly simplest of these structures, revealed a hidden landscape of chaos upon closer inspection. Astronomers discovered that its vast glowing ring is not a smooth, continuous veil of gas. Instead, it is littered with thousands of bizarre, tadpole-shaped objects, each one a miniature world of drama. They were named cometary knots, not because they are comets, but because their shape is uncannily similar, with a bright, glowing head and a long, dark tail streaming radially away from the central star. Each of these knots is a colossal structure in its own right, often larger than our entire solar system. They are not visitors from the outer darkness, but are instead the final, dense remnants of the nebula itself. These are clumps of gas and dust that were dense enough to resist being completely torn apart by the stellar wind. Now, they are caught in the unforgiving glare of the central white dwarf, and they are slowly being destroyed. The process is called photoevaporation. The intense ultraviolet radiation from the tiny, hot star is blasting the surface of each dense knot, boiling the gas away molecule by molecule. This creates the bright, ionized head that faces the star, a shield of superheated plasma. The gas that is stripped away is then swept back by the relentless pressure of the stellar wind and radiation, forming that long, dark tail that stretches out behind it. This makes every single knot a tiny arrow, pointing directly away from the source of its own destruction. The entire inner rim of the Helix Nebula is thus a field of cosmic tadpoles, all swimming for their lives against a stellar hurricane that will inevitably dissolve them. They are a breathtaking and sobering sight, a final granular stage in the dissolution of a star's legacy. Before the entire nebula expands and fades into invisibility, it first shatters into these countless fragments, each one telling the story of its own brief, defiant struggle against the light. This violent photoevaporation of the Helix Nebula's knots points to a deeper, underlying truth about stellar death. The very act of a star shedding its outer layers is not the smooth, elegant process we once imagined. For decades, the beautiful symmetry of many nebulae led us to believe in a uniform ejection, a gentle, spherical sigh into the void. But the reality is far more chaotic. We now understand that the mass loss from a dying star is almost never symmetrical. It is a fundamentally clumpy, lopsided, and messy affair. The culprit lies deep within the star during its final red giant phase. In its outer layers, massive bubbles of hot gas churn and rise to the surface in a process called convection, much like water boiling in a pot. But on a stellar scale, this is not a gentle simmer. These convective cells are colossal, and when they reach the star's tenuous outer atmosphere, they can literally blow massive chunks of the star's material out into space. Astronomers sometimes call this stellar asthma, a condition where the star does not exhale smoothly, but instead puffs out its material in a series of irregular, violent bursts. This creates an initial cloud of debris that is lumpy, uneven, and profoundly asymmetric. It is from this chaotic, raw material that the beautiful nebula must form. The fast winds from the emerging white dwarf and the intense radiation pressure then act like a cosmic sculptor, smoothing and shaping this initial, messy eruption. They carve the chaotic cloud, funneling the material and illuminating it into the more organized, bipolar or elliptical shapes we eventually see through our telescopes. The stunning symmetry of a butterfly's wings does not begin with symmetry. It begins with stellar turbulence, a violent and messy birth that is only later refined into the cosmic art we admire from afar. This stellar turbulence can sometimes lead to a dramatic resurrection. In a handful of incredibly rare cases, astronomers have witnessed what can only be described as a cosmic encore, a final act of defiance from a star that was supposed to be dead. These are the born-again stars, and they create the most bizarre nested structures in the cosmos. Take the planetary nebulae known as Able 30 and Able 78. In each of these systems, the standard sequence of events had already played out. The star had died, ejecting its outer layers to form a beautiful, expanding nebula. The hot white dwarf was left at the center, destined to slowly cool for eons, But then, something extraordinary happened. Deep within the white dwarf, a final reserve of unburned helium ignited in what is called a very late thermal pulse. This violent burst of energy reignited nuclear fusion right on the surface of the dead star. Suddenly, the white dwarf was reborn. It swelled back into a red giant, not for millions of years, but for a brief, violent flash of cosmic time. During this short-lived resurrection, the star ejected a new, slow-moving shell of gas. This fresh material did not expand into empty space. It blasted outward directly into the heart of the older, faster-expanding nebula that was already there. The result is a celestial Russian nesting doll. You see the faint, ancient outer shell from the first death, and then, glowing brightly inside it, a much smaller, denser, and younger nebula from the star's second death. This phenomenon completely upends our timeline of stellar demise. It proves that a star's death is not always a linear, one-way journey. For a fleeting moment, a star can cheat death, burning one last time to sculpt a final, complex monument to its own turbulent life. The star's very composition holds the blueprint for its final form. This was one of the most profound realizations in the study of planetary nebulae, a discovery that connects a star's entire life history to the shape of its death. Astronomers found a stunning correlation between the complexity of a nebula and a property known as stellar metallicity. Now, in astronomy, metallicity is a bit of a misnomer. It does not just refer to metals like iron or gold. It is a catch-all term for the abundance of every element heavier than helium. A star's metallicity is its chemical fingerprint, telling you what generation of star it is. The very first stars in the universe were composed almost entirely of hydrogen and helium, the pristine elements forged in the Big Bang. They had extremely low metallicity. When these ancient stars died, they seeded the cosmos with the first heavier elements. So, each subsequent generation of stars is born from more chemically enriched gas, inheriting a higher metallicity. Our own Sun is a relatively high metallicity star, a product of many generations of stellar death that came before it. And this chemical inheritance directly dictates the kind of planetary nebula it will one day leave behind. The correlation is striking. Older, low metallicity stars, which are often found in the galactic halo that surrounds our Milky Way's main disk, almost always produce simple, round, and spherical nebulae. They are the cosmic equivalent of a quiet, symmetrical sigh. But younger, high metallicity stars from the bustling galactic disk create a completely different legacy. They are the ones that sculpt the magnificent bipolar shapes, the intricate butterflies and hourglasses that captivate our telescopes. Why would the presence of heavier elements lead to such dramatic asymmetry? The answer lies in the physics of the star's final breaths. Heavier elements are far more efficient at forming dust grains. In a high metallicity star, as it nears death, its outer layers become rich with these microscopic particles of carbon and silicate dust. This dust acts like a powerful coolant, radiating heat away and allowing the outer atmosphere of the star to condense even further. This enhanced cooling and condensation leads to a much more extreme and much more asymmetric mass loss. The star does not just gently puff away its envelope. It experiences violent, dusty winds that are Chinese letter, shaped and focused by magnetic fields or a binary companion. The dust itself becomes a key player, a material that can be pushed by the starlight, helping to sculpt and channel the outflow into those spectacular lobes. So, the majestic butterfly wing is not just a product of a star's death. It is the final, brilliant signature of a star that was rich with the ashes of its ancestors, a cosmic inheritance written in light and dust. This ferocious sculpting of gas occurs at speeds that defy comprehension. We can measure the expansion of these nebulae, and the numbers are staggering. The outer shells are not drifting gently into the void. They are blasting outward at supersonic velocities, often between 20 and 50 kilometers every single second. To put that into perspective, that is over 100,000 miles per hour, a speed that could take you from Earth to the Moon in less than 3 hours. This incredible velocity is the product of a cosmic collision, a carefully staged accident known as the two-wind interaction model. The story begins with the red giant star. In its final millennia, it exhales a slow, dense, and massive wind. This wind is like a ponderous river of stellar material, flowing outward at a relatively sedate pace of just 10 to 20 kilometers per second. This creates the raw material, the initial cloud of gas. Then, the star's core is exposed as a white dwarf, and it unleashes its fury. This new, reborn star emits a second wind, but this one is completely different. It is a fast, tenuous, and incredibly energetic gale, screaming outward at thousands of kilometers per second. Now, imagine this fast, thin wind catching up to the slow, thick wind that was ejected earlier. The result is a collision of almost unimaginable force. The fast wind slams into the slow wind, plowing into it like a cosmic snowplow. It sweeps up the slower material, piling it into a dense, expanding shell and accelerating it to those incredible supersonic speeds. The boundary between these two winds is a violent shock front, a place where gas is heated to extreme temperatures and compressed into the sharp, bright edges that define the nebula's shape. This is not a gentle expansion. It is a supersonic traffic accident on a galactic scale, a carefully timed collision that forges beauty from chaos. But even that supersonic collision cannot account for all the missing material. When astronomers began to weigh the beautiful, glowing shells of planetary nebulae, they stumbled upon a profound mystery. They carefully calculated the mass of the visible gas and compared it to the mass a typical red giant star should have ejected to leave behind a white dwarf. The numbers did not add up. A staggering amount of the star's mass was simply gone, absent from the brilliant display. The visible nebula often contains only a small fraction, perhaps just 10 or 20%, of the material the star must have lost. This was the missing mass problem, and its solution pointed to a hidden, violent chapter in the star's death that we rarely get to see. The answer lies in a brief but cataclysmic phase known as the superwind. Before the star enters its final death throes and lights up the nebula, it undergoes an episode of extreme mass loss. This is not the gentle wind of the red giant or the fast wind of the white dwarf. It is a furious, dusty hurricane, a last, desperate expulsion where the star can shed as much mass as our entire sun in just a few thousand years. This superwind is so thick with newly formed dust particles that it completely shrouds the dying star. The dust acts as a cosmic cloak, absorbing the star's visible light and re-radiating it as invisible infrared heat. For optical telescopes, the star seems to vanish, hidden behind its own smoky shroud. It is only when this superwind phase ends and the central star heats up that the veil is lifted, revealing the now illuminated planetary nebula, which represents only the final, inner layer of the total ejected material. The vast majority of the star's mass was lost in that hidden, furious superwind, a dramatic prelude to the beautiful finale we are privileged to witness. That dusty shroud cloaking the dying star is far more than just a simple veil. When we finally peer through it with the infrared eyes of telescopes like Spitzer, we find a universe of microscopic complexity. The dust within planetary nebulae is not a uniform, cosmic soot. It is a surprising and varied menagerie of chemical compounds, each type telling a different story about the star that forged it. Some of these nebulae are veritable soot factories, incredibly rich in complex carbon-based molecules known as polycyclic aromatic hydrocarbons. These PAHs are sprawling, cage-like structures of carbon and hydrogen, essentially the basic building blocks of soot. In the infrared, nebulae filled with PAHs glow with a specific set of spectral fingerprints, revealing a cosmic environment dominated by carbon chemistry. Yet, in other planetary nebulae, the story is completely different. Their infrared signature shows a dominance of tiny grains of silicate dust. the same kind of stony material that makes up sand and glass here on Earth. This is oxygen-rich dust, a completely different chemical legacy. This stark division is not a random occurrence. It is a direct fossil record, a final message bottled up and sent into space that reveals the very last nuclear reactions that occurred deep within the star's heart. The composition of the dust tells us with certainty whether the progenitor star lived its final days as a carbon star or an oxygen-rich star. Here is how that cosmic chemistry works. During its red giant phase, a star furiously fuses helium into carbon in its core. For most stars, this newly created carbon remains trapped deep inside. But in stars of a certain mass, a powerful process called convection, like a giant stellar elevator, can dredge this freshly made carbon up to the star's surface. When this happens, the amount of carbon in the star's outer atmosphere can actually surpass the amount of oxygen. At that moment, the star is transformed into what astronomers call a carbon star. When this carbon star later dies and its atmosphere cools enough for dust to form, carbon atoms eagerly snap together into sooty chains and pHs, because there is simply more carbon available to form solids than oxygen. Conversely, if the dredge-up never happens and oxygen remains more abundant than carbon at the surface, then the available oxygen will readily bond with silicon and other elements, creating those silicate dust grains instead. So, the dust we see is a direct snapshot of the final chemical balance in the star's atmosphere. A carbon-rich nebula points to a star that successfully brought its carbon to the surface, while an oxygen-rich nebula signals a star that kept its carbon buried. The beautiful cloud is not just a shape. It is a chemical fossil, a last testament to the internal struggles of a dying sun. That chemical fossil, forged in the star's final days, now begins a long journey through the galactic sea. Planetary nebulae do not exist in a perfect vacuum. They expand into a thin but tangible ocean of gas and dust known as the interstellar medium. This quiet background of the galaxy is not empty, and when a nebula plows through it, the collision leaves a visible scar. In some remarkable cases, you can see a sharp, bright rim forming at the very leading edge of the nebula, a structure astronomers call a bow shock. This is the cosmic equivalent of the wave that piles up at the front of a speedboat. The expanding shell of the nebula, racing outward at tens of kilometers per second, smashes directly into the stationary or slower-moving material of the interstellar medium. The gas at this interface is compressed, heated, and set aglow, tracing the boundary of this colossal impact. This interaction does more than just create a pretty light. It actively reshapes the nebula's final form. The side of the nebula moving forward into the galactic wind meets resistance, slowing its expansion, while the trailing side continues to expand more freely into the cleared-out wake behind it. The result is a nebula that is no longer symmetrical. It can appear distinctly one-sided, flattened, or stretched out like a cosmic teardrop, elongated in the precise direction of the central star's motion through the galaxy. This discovery was a profound shift in perspective. It proved that the majestic form we see in a telescope is not solely a product of the star's death throes. It is a snapshot of an ongoing dialogue. The final appearance of a planetary nebula is a combination of its violent birth and the gentle, persistent sculpting of its environment. A monument shaped by both its past and its journey through the vastness of space. This journey through space is not always a silent film. Sometimes we get to watch it in real time. One of the most astonishing tools for this is a cosmic illusion known as a light echo. In a handful of fortunate cases, astronomers have witnessed planetary nebulae expanding before their very eyes, not by waiting for millennia, but by observing how light itself bounces through the dusty wreckage. The process begins with a flash, a burst of intense light from the central star as it undergoes a final, violent transformation. This pulse of energy races outward at the speed of light, but it does not just illuminate the main gas cloud. It also travels past it, out into a much larger, invisible shell of cold dust that was ejected long before the nebula began to glow. When this light pulse finally strikes those distant dust particles, they reflect it back toward us, acting like a cosmic mirror. Because the dust is much farther away, the reflected light takes a longer path to reach our telescopes. We see the main nebula light up immediately, and then, years later, we see a new ring of light appear around it, as the echo finally arrives from the more distant dust. This creates the breathtaking illusion of a ring expanding faster than the speed of light, a purely geometric trick that reveals the true three-dimensional structure of the star's surroundings. By carefully tracking the motion of these light echoes over just a few years, astronomers can do something previously thought impossible. They can triangulate the positions of these dust clouds, building a precise three-dimensional map of the entire system. This allows them to measure the expansion speed of the nebula directly, watching it grow in a human lifetime instead of inferring its history from a single, static snapshot. A light echo turns a beautiful picture into a living movie, giving us a front-row seat to the ongoing drama of a star's death. The serene image of a solitary, dying star is a cosmic fiction. For decades, the lone star model was the default, but it could never explain the intricate butterflies and multi-lobed structures we kept finding. A profound shift in understanding came with a simple but revolutionary census of the central stars themselves. Astronomers discovered that a staggering number, perhaps even a majority, of planetary nebulae are not powered by a single star at all, but by a binary system locked in a tight gravitational dance. This was the missing piece of the puzzle. The presence of a companion star transforms a gentle, spherical death into a directed, explosive sculpture. How does this celestial duet work so perfectly? As the primary star swells into its red giant phase, its outer layers become gravitationally vulnerable. The smaller companion star, orbiting close by, begins to siphon off this material. The stolen gas does not fall directly onto the companion. Instead, it spirals inward, forming a flat, spinning disk of superheated matter around the smaller star, an accretion disk. This disk becomes the engine for the nebula's complex shape. It acts like a cosmic gyroscope, stabilizing and channeling the erupting material. More dramatically, it can launch incredibly focused, supersonic jets of gas from its poles. These jets punch directly through the slower, expanding cloud of ejecta, carving out vast cavities and inflating the magnificent bipolar lobes we see as butterfly wings. Without that second star and its resulting accretion disk, the dying star's final breath would likely be a simple, round bubble. The gravitational tug of war and the focused power of those jets are what twist a sphere into a masterpiece, proving that the most beautiful deaths in the cosmos are often a shared experience. These concentric shells are the star's final diary, written in gas and light. Look closely at an object like the Cat's Eye Nebula, and you will see it is not a single, simple bubble. It is a cosmic onion with multiple layers of glowing gas nested inside one another, each a perfect, separate sphere. This beautiful complexity is a direct record of the star's violent, irregular death throes. It is the ultimate proof that the stellar asthma we discussed is not a single cough, but a series of powerful, separate heaves. Each distinct shell represents a different episode of extreme mass loss, a dramatic pulse where the star violently expelled a huge portion of its atmosphere into space. These catastrophic events were separated by long periods of relative calm, perhaps thousands of years where the star recovered, gathered its strength, and its outer layers settled back into a temporary equilibrium. Then, the internal pressure would build again, triggering another convulsion and the ejection of a new shell. The result is this stunning layered structure, a fossilized timeline of the star's final millennia. It is precisely like reading the rings of a tree. Each ring tells you about the conditions of a specific year, and by counting them, you can trace its history. In a planetary nebula, each shell is a ring, chronicling a specific, violent chapter in the star's demise. The intricate beauty of the cat's eye is not a peaceful scene. It is the frozen aftermath of a prolonged and turbulent struggle. A stellar life ending not with a single bang, but with a series of powerful, rhythmic sighs. Those layered shells are more than just a timeline of eruptions. They are a chemical record, a final testament to the nuclear fires that once raged within the star's heart. When astronomers began to analyze the light from planetary nebulae using a technique called spectroscopy, they expected to find a predictable mix of elements, a simple echo of the star's original composition. Instead, they found a bizarre chemical zoo. Some nebulae showed gas that was shockingly rich in helium and nitrogen, far beyond what should have been there. Others were veritable carbon factories with an overabundance of that fundamental element of life. These were not random anomalies. They were precise chemical fingerprints, each one pointing directly to a specific nuclear pathway that had been active deep inside the star during its final million years. The key to unlocking this mystery is a process known as dredge-up. Imagine the star's interior not as a static place, but as a churning, boiling cauldron. In its late stages, powerful currents of convection, like giant stellar elevators, can plunge deep into the core and then rise back to the surface. These currents perform a crucial task. They dredge up the freshly forged elements from the nuclear furnace below and carry them up into the star's outer atmosphere. This is how the products of the star's internal alchemy are brought to the surface, ready to be launched into space when the star dies. The specific elements that get dredged up tell us exactly which fusion process was dominant. The nebulae enriched with helium and nitrogen are a classic signature of the CNO cycle. This is a chain of nuclear reactions that uses carbon, nitrogen, and oxygen as catalysts to fuse hydrogen into helium. In the intense heat of a more massive star's core, this cycle runs efficiently, converting hydrogen into helium and, as a byproduct, creating a lot of new nitrogen. When a dredge-up event happens, it brings this helium and nitrogen-rich material to the surface. Later, when the star expels its envelope, that chemically altered gas forms the nebula we see. On the other hand, a nebula overflowing with carbon tells a different story entirely. This points to a final, frantic act of fusion where the star began fusing helium into carbon in its core. A subsequent dredge-up then carried that newly minted carbon up to the surface, transforming the star into a carbon star before its death. So, by simply reading the chemical signature of a glowing nebula, we can rewind time. We can determine whether the star was powered by the CNO cycle or by helium burning in its final days. The beautiful cloud is not just a monument to a star's death. It is a detailed autopsy report, written in the elemental language of the universe. These chemical autopsies reveal a star's inner history, but they cannot capture the raw violence of its final moments. The serene image of a planetary nebula is shattered by the discovery of high-velocity outflows, cosmic projectiles that scream through space. Beyond the main, glowing shell of gas, astronomers have detected material moving at speeds that defy belief, reaching hundreds of kilometers every second. These are not part of the general expansion. They are focused beams of energy, thought to be collimated jets launched with terrifying force. The most likely culprit is, once again, the gravitational dance of a binary system. As material from the dying star is siphoned onto its companion, it forms a superheated accretion disk. This disk can act as a powerful engine, channeling some of the inflowing gas and launching it into space in two narrow, opposing jets from its poles. These jets are not gentle. They are hypersonic bullets that punch directly through the slower-moving shell of the main nebula. They carry immense energy and momentum, carving out vast, elongated lobes, and often leaving behind distinct, bright patches known as ansae, which appear like glowing handles on either side of the nebula. These ansae are the visible scars, the points of impact where the high-speed jets are plowing into and shocking the surrounding material. This discovery completely upends the old story of a peaceful, spherical expansion. It introduces a new layer of directed fury, a phase of focused aggression that further sculpts and complicates the nebula's final form. The death of a star is not one event, but many, a series of eruptions and accelerations where unimaginable forces compete to write their signature on the sky. Even the most violent jets leave behind a subtle, structured silence. Deep within the cavities of these nebulae, astronomers have found a phenomenon of exquisite precision, a cosmic whisper that reveals the hidden geometry of the void. Using radio telescopes, they detected a strange amplification of specific frequencies of radio waves, a signal that seemed to be concentrated and intensified along the inner edge of the nebula's glowing shell. This effect is not random noise. It is a coherent, organized resonance, and its closest earthly counterpart is found in the whispering galleries of grand cathedrals or museums. In those architectural marvels, a person standing in one spot can whisper softly, and the sound waves, instead of spreading out, travel along the curved wall to be heard perfectly on the far side of the room. The physics at play in a planetary nebula are eerily similar, but on a scale of light years. The inner surface of the nebula's shell, a boundary between the hot, ionized cavity and the dense wall of gas, acts as a perfect curved reflector for specific radio wavelengths. As these radio waves are emitted, they do not simply fly off into space. Instead, they skim along this inner boundary, reflecting over and over again. With each pass, waves that are in perfect sync with the cavity's size reinforce one another, building in strength through a process called constructive interference. The result is a powerful, amplified signal at a very specific frequency, a clear shout from the edge of the emptiness. This whispering gallery mode is far more than a cosmic curiosity. It provides an astonishingly precise tool for measurement. Because the amplification only occurs for wavelengths that fit perfectly within the cavity, astronomers can use the exact frequency of the amplified signal to calculate the physical dimensions of the nebula's inner void with incredible accuracy. It is like measuring the size of a musical instrument by the precise note it plays. Furthermore, the intensity of the signal reveals the density of the gas at that sharp inner boundary, giving us a direct probe into the conditions at the very frontier where the fast wind from the central star collides with the slower, ancient ejecta. This radio whisper allows us to map the invisible architecture of these stellar tombs, hearing the shape of the silence left behind by a star's final breath. These cosmic whispering galleries are not the only structures that challenge our definitions. The universe has a habit of blurring the lines we so carefully draw. And nowhere is this more apparent than with a strange class of stars once thought to be a category of their own. Symbiotic stars are cosmic odd couples, a binary system where a puffy, cool red giant is locked in a gravitational embrace with a searingly hot, compact white dwarf. For a long time, they were simply seen as fascinating laboratories of stellar interaction. But then, a deeper look revealed something astonishing. Some of these systems were not just interacting. They were caught in the very act of creating a planetary nebula right before our eyes. In a typical single-star scenario, the nebula is lit by the central star's own radiation after it sheds its layers. But in these symbiotic systems, the process is a duet. The red giant is in its final stages, steadily losing its outer atmosphere in a dense, slow wind. This expanding shell of gas would normally remain dark and invisible for thousands of years, waiting for the red giant's core to be exposed and heat up. However, in this binary partnership, the red giant does not have to wait. Its companion, the white dwarf, is already incredibly hot and ready to go. As the red giant's wind flows through the system, it is bathed in the intense ultraviolet radiation pouring from the white dwarf. This external energy source instantly ionizes the gas, causing it to glow brightly, long before the red giant itself has finished its death throes. The entire system takes on the appearance of a planetary nebula, but it is one being powered from the outside in. This discovery completely erased the hard boundary we had imagined. It showed that a nebula can be turned on not just by a star's own transformation, but by a nearby cosmic partner. The formation is not a sudden event. It is a slow, drawn-out performance in an interacting binary system, a prolonged glow that can last for tens of thousands of years before the final act even begins. Yet even the most dramatic rebirths can have wildly different outcomes. The case of V605 Aquila stands as one of the most bizarre and extreme examples of a star's final flash. At the heart of the planetary nebula known as Able 58, this central star staged a cosmic comeback in 1919, suddenly blazing back to life in a brilliant outburst. Astronomers identified this as a very late thermal pulse, the same kind of resurrection we saw earlier, where a white dwarf reignites its fusion furnace. But V605 Aquila did something far stranger. When astronomers analyzed the new shell of gas it ejected during this final flash, they found a composition that defied all expectations. This fresh material was not a normal mix of stellar gases. It was composed of almost pure helium with barely a trace of hydrogen. This was a profound chemical puzzle. A star's outer layers are supposed to be dominated by hydrogen, the primary fuel of its entire life. For this new ejecta to be pure helium, something drastic must have happened during the final flash. The leading theory is as violent as it is fascinating. The thermal pulse, the sudden burst of fusion on the surface of the white dwarf, must have been so intensely hot and so thorough that it completely consumed every last bit of the remaining hydrogen fuel that was sitting on the star's surface. It burned it all away in a final, furious inferno, leaving behind only the helium ash. This helium was then blasted into space, creating a unique and short-lived chemical signature. This makes V605 Aquila a living laboratory. It is a rare chance to observe the absolute final stages of nuclear burning, a process that effectively cleanses a star of its primary identity. We are witnessing the last possible act of stellar fusion, a final, desperate consumption of fuel that leaves behind a stark and elemental monument to a star's ultimate demise. The final flash of a star's life even carries an echo of its galactic address. Far above the bustling disk of the Milky Way, where stars are born and die in rich, dusty spirals, planetary nebulae tell a quieter, older story. Astronomers discovered that these high-altitude nebulae, floating in the galactic halo, are fundamentally different from their disk-dwelling cousins. They are not the brilliant, intricate butterflies or complex hourglasses we often admire. Instead, they are typically larger, much fainter, and almost perfectly spherical. This is the galactic altitude effect, a clear pattern written across the sky that reveals the deep history of our galaxy's stellar populations. Why would a nebula's shape depend on its height above the galactic plane? The answer lies in the age and mass of the star that created it. The galactic halo is our galaxy's retirement home for ancient stars. These are population 2 stars, among the first generations to form after the Big Bang. They are old, slow-burning, and crucially, they are low-mass. A low-mass star lives for billions of years, but when its time finally comes, it lacks the energetic oomph to die in a dramatic, sculpted spectacle. Its final breaths are weaker, its winds are slower and more symmetrical, and it likely lacks a binary companion to twist its outflow into complex shapes. The result is a simple, round bubble that expands slowly into the near vacuum of the halo. In contrast, the planetary nebulae in the galactic disk are the children of a younger, more vigorous generation. These are high-mass, high-metallicity stars that live fast and die young. And their violent, chemically rich deaths are what produce the spectacular bipolar and elliptical forms. So, by simply measuring the size, brightness, and shape of a planetary nebula, astronomers can infer not just how its star died, but also how and where it lived for billions of years. This turns every nebula into a cosmic fossil, a single data point that helps chart the vast story of star formation and chemical enrichment throughout the entire history of the Milky Way. This cosmic recycling process, written in the deaths of countless stars, is also the ultimate fate of our own Sun. Its destiny is tied directly to the strange and beautiful nebulae we have explored. In about 5 billion years, our Sun will begin its own final, spectacular transformation. Having exhausted the hydrogen fuel in its core, it will swell into a brilliant red giant, its outer atmosphere expanding to engulf the inner solar system. Mercury and Venus will be consumed, swallowed by the star that gave them light. Earth will be scorched, its oceans boiled away and its surface rendered utterly uninhabitable, orbiting perilously close to the star's fiery outer layers. This is the violent prelude to a more serene, beautiful ending. After its red giant phase, the Sun will gently shed its outer layers into the void, creating a vast, luminous cloud of gas. For tens of thousands of years, this cloud will glow, a planetary nebula visible from distant star systems. At its heart, the Sun's exposed core will shine as a white dwarf, a dense, Earth-sized ember that will slowly cool over trillions of years. The very carbon forged in its final nuclear fires, the oxygen we breathe, will be returned to the galactic reservoir, destined to one day become part of new stars, new planets, and perhaps new life. Every nebula we see is a glimpse of our solar system's future, a reminder that the atoms which make us were once stardust, and to stardust they will one day return. From their misleading names to their vital role as galactic recyclers, planetary nebulae remain a constant source of wonder and surprise. These 28 strange discoveries have peeled back the layers of a cosmic truth. The death of a star is anything but a simple, quiet fade to black. It is a complex, often violent, and always beautiful process. It is a finale sculpted by the invisible hands of magnetic fields, a gravitational tango with a binary companion, and the final chemical signature written by the star's own internal fires. The next time you gaze upon an image of one of these cosmic butterflies, remember the incredible physics and history hidden within its glow. You are looking at the final, brilliant chapter of a star's life, a story of transformation written in light and gas. What other secrets do you think these stellar ghosts are keeping, waiting for the next generation of telescopes to uncover? Let us know your favorite nebula in the comments below. And don't forget to subscribe for more journeys into the mysteries of space.